Hi, everybody. Thanks for joining us. I'm Niall Buchanan with Broadcom, and I'd like to welcome you to our session today on the topic of zCX performance considerations. A lot of new and exciting advancements taking place, and the focus of our session today is the performance characteristics and considerations when running these container-based workloads on ZOS. If you have any questions during the webcast, please feel free to submit those through the chat window. We'll be having a Q&A at the end of the session. And with that, I'd like to turn things over to our speaker, Nick Matakis at IBM US. Nick?
Hi, I'm Nick Matsakis. We actually have two presenters in this presentation. I'm from ZOS development, so zCX or zCX, depending on which side of the pond you're on. Development in the virtual layer mostly. And Mike Fitzpatrick's the other presenter. He's an expert, an architect from the ZOS comm server area. There's a lot of communications involved with zCX as well, so we figured we'd do this together. So we did pre-record this session to make sure we finish on time, so on and so forth. So I'm going to let it rip now, okay? Thank you.
Hello and welcome to zCX Performance Considerations. Thank you for joining us today. My name is Mike Fitzpatrick and I'm an architect from the Communications Server Group in Raleigh. I'm joined by Nick Matsakis from ZOS Development in Poughkeepsie. Most of you are probably already familiar with the power of container technology on Linux. Containers allows for better application isolation, improved developer productivity by simplifying the configuration and startup of test environments, and better code quality because the container environment used for test will be the same environment for production. This technology is now available on ZOS via Containers Extensions, or zCX. What we would like to share with you today is some of the things to consider in order to get the most benefit when running your containers on zCX. Before we get started, I'd like to review some disclaimers. The measurement results we gathered and will present today were obtained using dedicated hardware and network resources. The applications used to drive benchmarks contain little or no business logic and were meant to focus on only the zCX and network infrastructure. So the measurement results we will show are only meant as a guideline. You may or may not see comparable results in your environment. We'll start off by providing a brief overview of zCX and review the major components of the function. Next, Nick will take you through some zCX tuning and capacity planning around memory and zip provisioning when you are ready to start configuring your zCX instances. I will then discuss some items to consider when accessing the zCX instances from a networking perspective, including co-location benefits. Nick will then show you how to monitor your Docker containers running in zCX by deploying and using the Grafana dashboard. And finally, for your reference, we'll provide a few links to more zCX materials as you continue your journey with zCX. Let's begin our brief overview of ZOS container extensions. ZOS's bread and butter workloads are the traditional OLTP and batch workloads that utilize subsystems such as CIX, DBT, or MQ, or a host of other subsystems and programming languages. But there is a need to bring applications and programming languages running on other Unix-like platforms to ZOS without the need to completely rewrite them from scratch. With the introduction of Unix System Services, a Unix-like environment was added to ZOS. This enabled the porting of applications from other platforms to ZOS with minimal effort and introduced new programming languages such as Java and C to the ZOS environment. But with the rapid adoption of containerized applications, the need to configure and maintain Linux server instances in addition to ZOS systems now becomes the next hurdle to deal with. With ZOS container extensions, ZOS now provides the next big evolution, the ability to run Linux on Z container images unmodified directly in ZOS. And it simplifies the rebuilding of your containers that might be running on other platforms to run in ZOS as well. So how is this accomplished? IBM provides and maintains a prepackaged Linux Docker appliance that runs as an address space within ZOS. Workflows for ZOSMF are also shipped to guide you through the steps to provision zCX instances. The existing Docker interfaces to deploy container images on Linux are the same interfaces you would use for deploying Docker images in zCX. This means, as a developer, there is no need to have ZOS skills in order to develop and deploy containers in zCX. Likewise, because the Linux Docker appliance is maintained by IBM, there is no Linux system administrator requirement to configure or service the built-in Linux kernel. In fact, there are no interfaces to be able to directly access the underlying kernel. Network access to the zCX Docker containers is through the z/OS TCP/IP stack. For communication with other address spaces, a cross-memory virtual network is provided. No external networks are used. For communication with other z/OS systems or systems on other platforms, a route over an existing TCP/IP network interface is used. I'll be providing some recommendations on an upcoming chart for this type of communication. And finally, because zCX instances run as address spaces in z/OS, the same operational procedures used for creating WLM policies and monitoring address spaces can be used for zCX address spaces as well. You have the flexibility to deploy more than one Docker container within zCX, as shown here, or you can configure and start more than one zCX address space per z/OS system. And one final piece, which we'll be discussing in more detail on subsequent charts, a lot of the processing to access the zCX Docker containers, as well as processing within the zCX address space, is eligible to run on zips. So zCX is another piece added to the z/OS equation. Diving deeper into the main components that make up a zCX instance, let's first start with the integration with z/OS storage. zCX utilizes the VirtIO Linux interfaces, which are well-defined, stable interfaces for virtualizing Linux. This allows zCX Docker containers to access storage that is owned and maintained by z/OS. The file systems and swap space used by the Linux kernel to support a Docker environment are created as vSAM datasets. This leverages the latest I/O enhancements such as built-in dataset or DASD level encryption. By hosting the data used by zCX on z/OS managed DASD, you can also take advantage of the existing resiliency features provided by GDPS, such as Hyperswap. You can include the recovery of your zCX workloads as part of your overall z/OS disaster recovery strategy. You do not need separate processes for recovering Docker containers in addition to traditional z/OS workloads, unlike what you would need to do if these Docker containers resided on Linux servers. Next, we'll look at how zCX utilizes a z/OS TCP/IP networking stack. Because zCX takes advantage of the VirtIO Linux interfaces, the Linux network can be virtualized such that it can access the existing network interfaces managed and provided by z/OS. Each provisioned zCX address space is assigned its own dynamic VIPA that is managed and advertised by z/OS's TCP/IP stack. Access to any Docker container running within a zCX instance is done using this dynamic VIPA. Because zCX uses a dynamic VIPA, if the z/OS system fails, the zCX instance can be restarted on any other z/OS system in the sysplex, providing a highly available container environment. All communication between a Docker container running in zCX and an external endpoint occurs over z/OS's TCP/IP stack. The z/OS TCP/IP stack communicates with the zCX instance over a virtual same-host link. There are two network types that are used for communicating with Docker containers. For endpoints that reside in the same z/OS system as a container running in zCX, a high-speed cross-memory virtual network is used for communication. For an endpoint that resides on a different z/OS or different platform altogether, an external network interface is selected. This selection is based on what the best available route to this endpoint is from the z/OS TCP/IP stack's perspective. In order to limit who can access the containers running in zCX, IP filter rules can be configured in the z/OS TCP/IP stack.
Yeah, hi, I'm Nick Mitsakis. I work in z/OS development. I've been working on zCX virtualization layer for about a year and a half now. I'm going to take you through configuration with regard to memory, CPU, capacity planning for zips, regular processors, WLAN policies, so on and so forth. Yeah, hi. Just stepping back for a minute. Remember, a zCX appliance or an instance of zCX, it's provisioned by z/OSMF, and then you start the appliance. When it started in a regular z/OS address space, just like all the other ones you know and love, right? And it's running Linux, right? And then within Linux, we're running Docker, And then within Docker, we're running one or more Docker containers. With regard to memory, when you provision the appliance, you specify how much guest memory you want us to use. So we allocate private above the bar storage, 64-bit storage, that's fixed for the guest. So that's the memory that Linux believes is real memory, and that's what it's using, right? It's virtualized, but it's currently in the field, it's fixed 4K pages. A little bit farther down in this presentation, I'll show that we're making an enhancement to that where you can use large pages, 1 meg or 2 gig pages to back the Linux storage. But that's regular storage that's managed by VSM, RSM. It comes out of the normal pools that other memory comes out of, and I'll talk more about that later. With regard to the virtualized CPUs, those are CPUs that Linux believes it has. Okay, the dispatchable units of work within the address space are TCBs, regular old NVS TCBs. Each of the virtualized CPUs run under a separate TCB. Okay. And then there's other work oriented towards, SRB traffic that has to do with inbound traffic from IP, okay, and also I/O that we're doing to the vSAN datasets that are backing the Linux file systems. All right. The majority of the dispatchable units are zip eligible. So all of the virtual CPUs that are running as TCBs, those are zip eligible. So they're going to run on zips if you have the capacity, okay. Unless there's some function that it's doing that has to run on a regular processor. In general, there's not much of that at all. All right. The I/O to vSAM, that actually is not zip eligible at this time, but our internal benchmarks show that it's minimal, okay, because we don't do much work there. Our internal benchmarks show like 95% or higher zip eligibility. So that's what really you should expect, okay. Now, with regard to WLAN policy, because we're just a regular ZOS address space, that we actually don't provide any type of transactional understanding. So it's an address space that you're managing with velocity goals. So you can use a WLAN service class. You can set the importance level for it. It's an STC. It's classified an STC. You can specify the velocity goal, the velocity you want for each of your appliances. You can turn on the normal functions, I/O priority queuing. You can use a resource group, whether it's a normal resource group or a tenant resource group, to cap the amount of CPU you want it to use. Whether you want the zip processors to flow over to regular processors. Of course, there's the overall IIP honor priority queuing for the whole system as well, but you could also control that at a resource group level. You could also limit how much real memory you want the appliance to use. Now, remember I said that you define how much memory the appliance uses as guest memory, but as a systems programmer, you may want to also cap either a particular instance or with a WLAN resource group, maybe multiple instances. So in case somebody else is doing the provisioning, that might not be you, right? They may make a mistake and they may choose too much memory. So you can actually cap the memory via the WLAN resource group so that someone can't use more than what you had planned for. So that's a nice feature. Okay, given that it's the guest memory is fixed memory, what that means is if they try to get more memory than what you define, we'll actually fail the initialization and we'll put out a reason. We'll say, oh, we hit this limit, and we'll tell you what the current value we were trying to get and what the resource group value is. All right. Now, with regard to monitoring from a ZOS perspective, it's a ZOS address space. You can use RMF to monitor it. We cut the normal SMF records, SMF30 for the address space. You get the whole gauntlet of 70 through 78s if you all the RMF monitoring, so on and so forth. So that's really nice, okay? And you can use that for capacity planning and monitor the address space just like you've done before. So now you sit back and say, how many CPUs do I need? How many virtual CPUs? They're defined when you configure the appliance, right, via the ZOSMF workflows. But determining how many you need, it's really a function of how much power do the containers need that are going to be running in the appliance. Some of the containers might provide guidance on how much CPU utilization or memory that they use, right? Others may be containers that you already have deployed elsewhere, so you have an understanding of how much they're consuming elsewhere and how that would relate to System Z resources. So given that, it's probably going to be trial and error, right? And also it depends on what your goals are, okay? But definitely don't define more CPUs, then you have zip threads on the LPAR. And SMT2 plays into this, so it also counts SMT2 threads. How much of the appliance is eligible, zip eligible? IBM internal workloads have showed that somewhere around 98% of our workloads, a couple of workloads that we run, were zip eligible. So I think a good rule of thumb, what we're saying, is that 95% of what you're going to run, rule of thumb, would be zip eligible. So you can start with that and see how you go. But you really have to be careful about zip consumption. As more and more people are exploiting zips, and some of those people are actually critical middleware or applications. For example, DB2, if you turn on zip enablement for DB2, it turns all of its enablement on, including zip eligibility for log writes. Okay, so the back-end processing of log writes is done under zip processors. So you need to make sure, so that's considered low latency work, right, because it's critical and important. So you have to make sure you have enough capacity. I'm going to recommend taking a look at Martin Packer's zip capacity and performance presentation that he put out a couple months ago. A team of experts, including myself, looked at that presentation to make sure it was current and provide some good guidance. You could do a web search on him. Also, the URLs in the notes section of the presentation. Okay. The other important thing is IIP honor priority. So you can set it in IA opt for the system overall. You probably already have that set. That determines whether zip eligible work that is not getting the performance that's required can run on regular processors or not. Okay, you may want that on, you may not want that on. In general, we want it on, right? If you have important work. If you have a test zCX guest where you don't want it to impact your others on the system, you may choose via the WLM resource group definition to turn that off so that that particular appliance does not impact others by consuming GCP. Also, as you know, GCP cycles, right, increase your software costs, so it's not something you necessarily want to do. So planning is critical. Definitely keep an eye on the RMF APPL percent IIPCP, which effectively tells you how much zip eligible work was running on regular processors, which means you didn't have enough zip capacity, right? But for the third time, make sure you have enough zip capacity at peak times overall, because you don't want to impact others that are running on the system. So what is zip eligible? All the virtual CPUs, we already covered that. They're running as regular MVS tasks. All of those are zip eligible. 98% of the time, 98% of the time, they're definitely running on zips. Okay. SRB processing for TCP/IP traffic when IWQ is defined is also zip eligible. If you're not using IWQ, then it's not zip eligible. What's not zip eligible is the IO completion processing. So the SRBs coming back in from vSAN, those are not zip eligible, but they're not CPU intensive anyway. They do very little. Most of what they're doing is waking up or actually presenting an IO interrupt back to Linux. So they queue something, they basically cause an interrupt on one of the TCBs. Okay? When it comes to memory, it really is a function of what you're going to be running in the appliance. So you have to understand which containers you're going to run and what their memory demands are, and then add 1 gig for zCX. Within that memory, you need to calculate how much of it should be real and how much of it should be swap file. From a performance perspective, the more real, the better, right? But of course, you're using real resources. See the zCX documentation for rules of thumb on how to calculate how much real and how much should be swapped based on the memory demands. You really want to make sure you have enough memory so functionally it works, but also Linux itself is not paging. When it pages, it's going to consume CPU that you would rather it didn't consume. Also be aware that Docker has controls on a container basis for limiting how much CPU and how much memory can be used. The memory that's used by zCX is not susceptible to the normal virtual storage memory limit that you may know and you're probably using already on your system. Currently, zCX can only use 4K fixed pages to back the guest. We have an APAR coming out in September, OA 59673, which allows you to use 1 meg fixed pages or 2 gig fixed pages. zCX can only use preferred non-configurable real storage from either the 2 gig fixed page size area or the 1 meg 4K preferred page size area. So it can't use the non-preferred storage area. And that's important to understand when you're doing capacity planning for guest memory. Okay. And if you're using 2 gig storage, it has to come from the 2 gig area. If you're using 1 meg or 4K fixed frames, SRM has controls via IA-opt-XX. There's the IRA 405I 2 control, which basically says when will SRM issue the IAR 405I message to indicate that you've fixed more storage than the threshold that you defined or the system defaulted to. And then there's the MCC FXT PR, so the fixed percentage value. And SRM will start to take action by swapping out address spaces when you get close to that limit. The default is 80% for up to 250 gig of storage. Above that, it's a higher percentage. But again, SRM will start to take action maybe at 72% for the 80% or 73%. And that action could negatively affect other address spaces that are running on the system by swapping them out, making them non-dispatchable. Okay, and that can really hurt. So you really have to do proper capacity planning and possibly tweaking these parameters in IA-opt. Especially if you're on a test system, you're probably going to hit those values. I've seen several customers do that already. Or maybe if you're on a development system where you may be using more fixed storage than normal, okay? This chart covers some display commands that you can use to determine how much memory you actually have on the system that could be used by zCX. So the first command is display m equals store. And you can see in the orange, circled in the orange, you want to look at non-reconfigurable storage, right? So that's the preferred storage. So in this case, adding up those two ranges, you can see we have 788 gig of non-configurable preferred storage. So that's what zCX can use for 1 meg fixed or 4K pages, all right? And then to get the LF area information, there's a modify command that you issue against system recs to run an RSM exec called IAXDmen, and it shows the display on the right. So if I go through this display, at the top it has pageable 1 meg pages. We don't use pageable storage, so it's not related to us. But that does indicate how much storage is actually in use, but it's pageable, right? So it's the fixed storage, but it's in use, it's important. In the orange, it's showing how much 1 meg fixed storage is in use, right? So that's going to tell you what the available value is from the LF area, and then also how much is used. And then for 2 gig storage, which we can only use if you're using a 2 gig frame size, right? With that APAR that's coming in September. This tells you what the LF area definition is for 2 gig and also how much is in use. zCX's most recent performance improvement SPE is now available via APAR OA 59573. Just became available at the end of September. It provides the ability to back the Linux guest per address space, so you can choose which appliances you want to use this function for, with 2 gig pages or 1 meg pages rather than 4K pages. So you can use any of the 3 sizes. The bigger the page size, the better performance you're going to get. 4K pages provides the worst performance, and I'm going to talk more about this later as to which size would you pick. But just think 2 gig gives you the best, right? 1 meg gives you good performance, and 4K gives you the worst performance. All right. So why is that? 2 gig and 1 meg pages have been supported by z/OS for a while now, depending on the function or the middleware. For example, DB2 supports 2 gig or 1 meg pages, pageable or fixed, for its buffer pools. Java supports 2 gig. 2 gig are always fixed, by the way. Okay. Java supports 2 gig fixed or 1 meg pageable. zCX requires at the moment that all the pages that are used for the guest are fixed. So 1 meg pageables doesn't play here, nor does 4K pageable. All right, so where are you getting a benefit from? So there are two aspects to this. The first is when you have a large page, the data address translation tables that are used to translate a virtual address to a real address don't need to be as long. or as big, right? So if you have a 2 gig page, for instance, you effectively have a whole region within that one page. So translating the virtual to real is just get me to the real, and then I just use the offset of the latter part of the virtual address within that real page to actually find the address that I'm referencing. So you save storage, real storage, within the LPAR by reducing the size of the DAT tables. So that's the first thing. The second thing is each CPU has a shortcut for a particular virtual address to get to the real address. And that's the translation look-aside buffer. However, each CPU only has so much space, just like all caching type of buffers, okay? And there are different ones. There's a 2 gig TLB, there's a 1 meg TLB, and there's a 4K TLB area, okay? So when the translation of a virtual address to a real address is within the cache or the TLB buffer, it's really fast. If it's not, it has to run the DAT tables. All right. So 2 gig pages are going to help you in two cases, right? You have less TLB entries, so there's a greater likelihood that your address translation is going to be in the TLB buffer. And also, if it's not, it's much faster to get to the real page because the DAT tables are smaller. So 2 gig pages, 1 meg pages, it's a win-win in general. So from a performance perspective, you want 2 gig or 1 meg, 2 gigs best. Now, don't get Linux huge pages confused with this support I'm talking about. The support I'm talking about is specifically the storage that's used to back the guest, which we call guest storage. All right, so that's the storage that Linux believes is real memory, right? Because we're playing hypervisor. Within Linux itself, it has its own DAT tables. So even though it's running under hypervisor, it's still managing page tables, okay? And huge pages is Linux implementation of large pages. Currently, with zCX, we don't support, or we tell Linux basically that the machine it's running on does not support the technology for them to support huge pages. That's where we are right now. In the future, that might change, but as of right now, that's where we are, okay? So don't get the two confused. All right, so with large pages, most workloads, the two main workloads that we run, showed significant benefit, all right? However, rarer, and I'll say rarer, small memory footprint workloads may show little benefit. For example, we were doing some tests with ComServer that was really focused on a particular transaction. I wouldn't even call it a transaction, right? But a particular case where they're just sending a message between A and B, between zCX and the host, and they're doing the same memory size all the time, and it just does it over and over and over again because they're trying to measure how fast is that path. Well, that path is always touching the same memory every time. So even with a 4K page size, it performed just as well as with a 2 gig page size because it's only touching a small amount of memory, right? It might be like, 1K, and that fits beautifully within the 4K page size. So I'm going to say real workloads, you're going to see a lot of benefit. Some real workloads that are rare, that might have a small memory footprint, you might not see as much benefit. So looking at the table that I have here with some of the internal benchmarks, first of all, there are two different categories if you're not familiar. On the right, ETR is external throughput rate, and that's basically the transactions per second, okay, external throughput rate. The ITR is the internal throughput rate, and it's a function of the ETR, so how many transactions you're doing, how much work are you doing, and how much CPU are you doing. So it's possible that you could keep the ETR steady, right? And you use a lot less CPU, so your ITR goes up. All right, and that's the golden thing. I mean, we keep a close eye on ITR because we want to use less CPU per transaction. Okay, we also want to be able to scale transactions, so you want to have an ETR that can scale. So looking at this table, you can see that with 2 gig pages, we got significant benefit in our workloads, up to 13%, and ETR benefits up to 6% with 2 gig pages. 1 meg pages isn't, it's not shabby. It's pretty good, right? You can get up to 10% in our workloads in ITR and 5% ETR. In the last row with 4K pages, this APAR not only provides the ability to use large pages, but it also has some more hypervisor improvements, I'll say, okay? But that is also a function of which functions the workload is using. So it could be that you don't get any benefit. And in the two major workloads that we use, they both saw benefit. One has MongoDB in it. It's an Acme Air workload. That one actually saw more benefit. So how do you pick a page frame size? 3 things to consider: best performance, flexibility, and planning. 2 gig pages by far gives you the best performance. I talked about TLB and dat tables. Also think about other workloads that could be running where you're not displacing as many TLB entries. You're not impacting them as much. But it is the least flexible. In order to change the 2 gig large frame area, it requires an IPL. Looking at the picture, all the way on the left side, you can see that the 2 gig pool is a fixed pool, okay, and it can't be changed unless you IPL, so you have to plan for it if you don't have enough storage. Plan means you need to plan a planned IPL. If storage consumption is an issue, then it may not be the best choice for instances that come and go, as others may not be able to use 2 gig memory. So for instance, if you have an appliance that's up during the day, and at nighttime you want to run, let's say, some batch workload, and the batch workload can't take advantage of the 2 gig memory, then 2 gig is not your best choice for that scenario. Unless, of course, you have enough memory, then it doesn't matter. You can't use 2 gig pages on ZVM if you're running ZOS as a guest. 1 meg fixed pages provides really good performance, much better than 4K. It's noticeably less performance than 2 gig though, right? It reduces TLB entries, all that stuff, but not as much as 2 gig. It's a screamer on ZVM. If you're running ZOS on ZVM, whether it's sandbox or not, definitely use 1 meg. It's the difference that I see on my appliance. I got an 8 gig appliance. It's a difference between 20 minutes and 20 seconds. And I did say minutes. Provides good flexibility. Looking at the picture down the middle, right? The preferred storage pool is where zCX is at. That pool can be either 1 meg or 4K pages. All right, so it gives you that flexibility without an IPL, right? That pool is used. The only problem with 1 meg pages within that area is the LF area parameter. The LF area defines 2 gig pages that are carved out at IPL time, but it also provides a maximum for 1 meg pages. Okay, and it's a maximum only as of ZOS 2.3. It used to be, prior to 2.3, there used to be a separate 1 meg fixed and 1 meg pageable area. So unfortunately, you may have to do an IPL in order to change the LF area for 1 meg pages. If you do change that, I recommend that you just crank it up, okay, because it is a maximum. Beware that others who wanted to use 1 meg pages will now start to use 1 meg pages because you've provided them with that ability. You may even get better performance, not just for zCX, but for others. But I say beware because you need to take a look at what's being consumed. You may want to do that before you even bring up your zCX appliance. 4K pages, worst performance, not recommended as first choice. Sandbox only, no production, okay? First choice. Best availability, two reasons. It could be that you have so much real memory fragmentation that we can't find enough 1 meg pages, all right? It's a really good choice to have at the end of the list. zCX allows you to choose, starting with the largest page size to the smallest page size, which one it should attempt. So if you did 2 gig, 4K, it's going to do 2 gig if it can find them. If it can't find 2 gig, it'll go to 4K. I also recommend that you automate to the messages that zCX puts out, or the message that it puts out when it can't get the page frame size that you wanted. So for instance, if you did 2 gig, 4K and you couldn't get 2 gig, you want to know, because that means you're not getting the performance that you wanted to get, even though the appliance is up. So for availability, that's great, use 4K, but you're not getting your performance, you didn't do proper planning, or the world's complicated. It could be that when you started it, there were others that you didn't know were going to be there and you didn't have enough memory. Being current on service, especially with zCX, because it's relatively new and we're providing performance improvement in a dynamic fashion, we're concurrently doing it, okay? And we have other future performance items that we're going to be shipping probably within the next year or so. So really keep an eye on the latest service for performance. Make sure you have some of the APARs that I'm mentioning here, OA 58296, Came out in February. If you don't have that on, I don't even want to talk to you, right? Okay. It's one of those you really have to have on. It has a lot of really good benefits. The more virtual CPUs you have, the better the performance you're going to get, and it's pretty dramatic. You can see, and here I have a 50% ETR improvement, double-digit ITR. So, got to have that on. It's been around for a while now. The other major one is OA59111. It provides SIMD or vector support instructions. So if you have any scientific type applications, AI, all that kind of stuff, you're going to get a lot of benefit from that. And I talked about the large pages, beat that one to death. It's available as of the end of September.
I'd like to continue with some considerations when configuring your network environment for zCX. In an example workload configuration, suppose that clients access an application or service residing in a Linux container. This application or service then needs to communicate over an external network to a database subsystem running on z/OS to complete the transaction. This network communication between tiers can be costly, especially if it requires a lot of chattiness between the application and data tier in order to satisfy a single transaction request. When considering whether to take advantage of the Linux Docker container environment provided by zCX, your goal should be to keep the container co-located with the z/OS database, if at all possible. By utilizing the cross-memory virtual network, you can reduce the overall network latency between the application and data tiers that can negatively impact the response time for your transactions. In testing done in our environment, we configured a client Docker container application running on a Linux server, communicating with a server application running on a z/OS system. Both the Linux server and z/OS system were on the same subnet. We then compared that to the same client application on a Docker container running in zCX, co-located with a z/OS server application. For interactive workloads with smaller transaction request and response payloads, with zCX, we were able to reduce response times by 45% while increasing transaction rates by over 80%. For workloads that stream data, network latency was reduced by 67%, while throughput more than tripled in the co-located environment. For workloads that stream data, we can perform additional steps to provide even more optimizations in a zCX environment. Because we are utilizing the cross-memory virtual network for communication when zCX instances are co-located with their endpoints, there is no physical limits imposed on the size of a packet that can flow over this network. So if you have a workload with large transaction payloads or that streams data between the zCX Docker container application tier and z/OS database tier, configuring a larger MTU using z/OSMF workflows for zCX and the TCP/IP profile for z/OS, you can reduce the amount of processing that would occur versus having to handle the sending and receiving of many smaller size packets. In our test environment, we compared a configuration using the default 1492 byte MTU versus a configuration where a 64K MTU was used. With the larger MTU size, network latency was reduced by over 40% and the throughput increased by 80%. And because there was less packets to process, z/OS utilization on general purpose processors was reduced by 34%, and zCX and Docker container utilization on zips was reduced by 60%, helping to decrease the need for additional zip capacity when running containers in zCX. There may be scenarios or conditions where a Docker container running in zCX cannot be co-located with the z/OS database. In these scenarios, there are still optimizations that can be made to make the communication over the external network as efficient as possible. Inbound workload queuing, or IWQ, is an OS Express feature that allows inbound packets to be separated based on workload traffic type. When configuring IWQ and using zCX, any inbound packets destined to a Docker container in zCX would be separated from packets targeting other z/OS applications. This separation allows for better ordering of packets being delivered to zCX, thus reducing unnecessary retransmits due to any out-of-order delivery. This separation also enables the z/OS processing of these inbound zCX packets to be scheduled to run on zips. In testing done in our environment, we compared an interactive workload running in a configuration not using the IWQ function with a configuration that did. With IWQ enabled, better batching of packets and preservation of packet order is achieved, and we saw a reduction in response times by over 25% and improved transaction rates by 34%. And because we are able to schedule inbound ZOS processing on zips, about 40% of the ZOS network processing for the workload can be moved to these zips. The key takeaway is to make sure you have the latest communication server maintenance applied for zCX. TCP/IP APAR PH16581 and VTAM APAR OA58300 provide the IWQ enhancements that improves the efficiency of processing packets for zCX, as well as making this processing zip eligible.
All right, so this section, we're going to talk about Docker performance monitoring. So, I mean, you have your normal monitors for normal ZOS address spaces, but remember you're running Linux in there. And within Linux, you're running Docker. So there are a set of Docker performance monitors that are available. I'm going to highlight some of the ones we recommend here. Right, for monitoring Linux, zCX provides a sample Grafana dashboard for monitoring the appliance and Docker containers. Okay, so that's important. You look at the appliance overall, so Linux overall, and then also each individual container to see how much resource they're consuming. The example, in order to use Grafana, there are 4 different components that are required. So you have to install all the components. Grafana provides the visualization. Node Explorer exposes metrics about the Linux operating system. cAdvisor exposes metrics about the containers. And Prometheus collects the data, okay, that is used by Grafana. So Grafana takes the data out of Prometheus, and Prometheus is taking the data out of cAdvisor and Node Explorer. See the link for updated instructions on how to run the monitoring tool. So you have a nice link here that tells you about it. And the zCX Grafana dashboard template can be obtained from that URL. There are also instructions in the zCX Redbook on on getting started with ZOS container extensions. So there are instructions on how to install the monitoring parts, obtain the adjusted zCX sample dashboards, create your own dashboard. But beware that the links with instructions on how to run zCX Grafana dashboard are more current and should be used. So what that means is the Redbook's down level. So you can still use the Redbook and go through it, but how to finally do the install and run the monitor, you should use the link. This is an example of one of the Grafana dashboards that we ship with zCX, or at least we ship it. You can download it. Okay. So if you take a look at this dashboard, you can see the appliance CPU utilization. Right. You got a nice number up there. Appliance physical and used memory, buffered and cache memory, the amount of disk that's being used, how much swap space is being used. Remember, we don't want swapping, so I like that 0%. You start swapping in Linux, the performance is not going to be good. Okay, but there's a nice dashboard here, so you can see memory usage over time. So there's the current usage, how much was used over time, network traffic, disk I/O reads, disk I/O writes. Okay, averages over time. This is another example of one of the dashboards, but this time it's at a container level. So if you look at the container CPU utilization, it shows you over time, right? And then to the right of it, you can see it has cAdvisor and Grafana itself. Okay, and then IBM, zCX, ZOS, SSH. So someone's logged in, SSH, we always have that container up. SSL registry, so on and so forth. You can see the average and the current CPU utilization. To the right of that, you can see how much memory is being used. So this time we have max and average. Right? Network traffic, I/O. Okay. This chart illustrates an example of being able to set up a monitor for multiple appliances on potentially different systems. All right. We don't actually ship this example, but it's something you can set up. And so the key points here in the lower left, you can see that the actual user is interfacing with one instance of Grafana, who's interfacing with one instance of Prometheus. And Prometheus is reaching out to cAdvisor on all the appliances, or in this case, the two appliances to the right. And also Node Explorer, where it's getting information for Docker, from Docker and also from Linux. So you can do that over the network. So it's a pretty simple thing to do. You should be able to set that up if that's what you want to do. So one-stop shopping for all your appliances, or different sets of appliances for different team members, so on and so forth. This chart has reference material, some of the topics we've discussed, and go into greater detail. Some we haven't actually discussed. The first one, this comm server puts out a performance summary report periodically, and they modified it for zCX. So it has performance numbers for internal testing for different packet sizes, rates, so on and so forth. Using zCX is very good from that perspective for performance. The second one is a white paper that's put out by the IBM IT Economics and Consulting group. And they did a study and benchmarks with regard to real customer applications, if you will, and the cost of ownership. So they have performance numbers and then they have costs. So they were comparing ZOS using DB2, different types of applications, microservices, so on and so forth, against x86. So it's excellent. Okay, zCX documentation is good for determining the guest memory size. It has procedures for doing that, equations, and also the swapper file. So it's good for that. The zCX Red Book, this Red Book is getting a little old now. It's good. The only thing to watch out for is the Grafana dashboard setup. My charts had more recent information on how to do that. Otherwise, the Red Book is good. The workload manager. So two things, right? Velocity goals. That's how you're going to manage each of these appliances. So service class definition, so on and so forth. The ways of using resource groups, WLAN resource groups, to limit zip to GCP capacity, how much memory you're going to use for the service, not the service class, the service classes that map to the resource group. So you can use a memory limit, for instance. There are also two relatively new hot topics articles that are good. Rapid containers improving zCX performance, runtime performance, and then running zCX on IBM Z Docker containers inside ZOS. Just do a search on those. They're good to review. They provide some good information. So this is the end of the session. Please remember to provide feedback for the session. Since it's an online conference, you can do that online at the URL provided at the top.
And it's also the charity giving.
All right, Neil. So I guess we take questions now.
Yeah. So
go ahead.
Everybody can unmute themselves if they want, or you can use the chat for question and answers. Any questions?
Thought I heard something, but I don't know.
It sounded like a dog.
We'll take questions from dogs too, whatever. All right, so no questions, huh?
Doesn't look so.
Okay. All right, so want to wait a little bit longer, or how many people we have left?
We've still got 14 people on.
Okay, so just so everybody knows, we finished the session. So if you have any questions, can we ask a question maybe?
Hey, you can ask a question.
Is there anybody running zCX currently who is happy, not happy, knows how to spell it?
You got a response from Philip Richard. Yes.
All right. Okay, Philip. Oh, with an exclamation point. So is that good? Is it a good exclamation point? Yeah. Okay, great. So is there anything? There's nothing in this presentation that you learned? I mean, the large page sizes is new. Can I ask you, Philip, are you actually using it?
You can unmute yourself, Philip.
and thank you for responding.
Okay, so I'm muted mode now. Yeah, I'm using zCX, but at the moment I'm using it running under ZVM, and I didn't know about the options to actually make use of the 2 GB page frames.
Right.
That's something I'm going to look at,
Okay.
especially running at the ZVM. It should help the performance a lot.
Yeah. Okay. There's one thing with the ZVM that I didn't mention.
Mm-hmm.
In its forthcoming, we haven't finished it, which is annoying. But in order to use the 1 meg page, so you can't use 2 gig on ZVM. I mentioned that.
Yeah.
In order to use 1 meg, there is a problem in ZOS that you don't actually get all the 1 meg pages that you want until that problem is fixed. And it has to do with the storage increment size that your guest machine on ZVM. So the CP definition is defined, and there's a way to get around that. And what you have to do is you have to define the storage with a standby option. So if you look at the define store command in VM, normally you do a define store and like whatever you want, right, for the guest, like 16 gig or whatever. There's another keyword, so it's define store space, whatever you want, space, standby, and if you specify 1 meg, then you'll get a storage increment size that's greater than 1 meg. ZOS has a problem with the storage increment size of 1 meg, and the only place you get that is when you're running under ZVM. And a normal LPAR, you're never going to get a storage increment size of 1 meg. So what ends up happening is ZOS says, oh, I can't get you all the 1 meg pages because of that storage increment size, or you don't get the performance that you want. So I'll say it one more time. You have to do a define store, right? What you normally do, space, standby, space, 1 meg, 1 and then an M. And that'll get you the storage increment size that you want, and things will be great. And I think you probably noticed it takes a while for Docker to come up. And like
yeah, correct. Yeah, not
example,
only come up is okay, but the some of the container operations takes ages. Like for instance, I tried to run Zoe under zCX, the CLI, and the performance was very poor, very poor.
Yeah, so hopefully, actually, I'd like you to tell me. Like the example I told you, when you come up, there's a difference between in my 8 gig guest, it takes 20 minutes just for Docker to come up using 4K pages. And this has to do with the ZVM itself does not support 2 gig pages to use itself, right? It allows guests to use 2 gig or 1 meg, but it's really using 4K. So it creates these shadow block things. And doing that conversion, it's just slow as hell. So now I come up like 15 seconds, maybe 16 seconds compared to 20 minutes. It's dramatic. So I'd be very interested to know if your Zoe container is also faster. That I don't know, but if you give me some feedback, I'd love to know.
Sure.
So you define 1 meg and then you do the def store like I told you?
Yeah.
Okay. Anybody else? Or you have any more questions, Philip, or anything else to comment on?
No.
Okay. Any other questions? Okay. Anybody want to raise their hand? Oh, go ahead.
So I think we'll close it up now then, folks. Unless there's any more questions.
Thank you very much, Nick.
Okay, you're welcome.
And don't forget to fill in your feedback forms, please.